Welcome everyone to the Advanced Material Forum Europe. We are excited you have joined us for this virtual forum event. Unfortunately, due to the coronavirus restrictions and to keep everybody healthy and as safe as possible, we decided to host the online forum session from our home offices here in the Netherlands. If you have any questions during this session, you can submit them via the chat function and we will answer you as soon as possible. Thank you for viewing my presentation. My name is Jansen Lau, and today I would like to discuss with you a topic related to understanding why and how thermoplastics react to automotive fluids. This presentation will take approximately 45 minutes and intended for you who would like to know a bit more on the durability of plastics in automotive applications, especially in view of their performance in chemical environment, typically present in such applications. I will start my presentation with a quick reminder of different types of plastics for automotive applications, followed by some discussion related to chemical resistance study that we have been doing at DSM regarding the plastics applications in automotive. And I would also want to end my talk with a discussion on what better chemical resistance of polymer allow us to do. Why we use plastic for automotive applications? There are at least several reasons to do so. The most important one is to use plastic as a metal replacement. This is related to the weight reduction of car and also lowering down of greenhouse gas emission that is currently and in the future also being regulated more and more. There are several choices of plastic materials, as you can see in the right-hand side figure. Usually plastics categorized as advanced engineering plastics, engineering plastic, or standard plastics. You can choose one of these plastics for your applications. But in order to choose the proper materials for this, we need to understand first the durability of these plastics in automotive environment. In essence, plastic can be found in two forms, either as a thermoplastics or thermosets. So thermoplastic polymers typically has a lower molar mass. It's soft or can be found as a ductile or brittle materials. And this is the type of plastics that usually applied via injection molding. And you can find it most of the time for under the hood applications for automotive. The second part is thermosets. So this is type of plastics or polymer that has a high molecular weight. It is hard brittle. Usually also applied via thermal or UV curing. And this is type of plastics that you find as a paint or coating for automotive in general. If we are talking about durability of plastics in automotive environment, there are three things that that pop up to mind. So the first one is related to thermostatic stability. The second one is related to chemical resistance. And the third one is related to UV resistance. So this is important for plastics that is used for outdoor applications. So today we focus on the chemical resistance. And speaking about chemical resistance, usually we are faced by the behavior or resistance of plastics under high temperature, high humid condition, high acid or alkaline environment, as well as the presence of additive that is typically used in automotive fluids. As a definition of chemical resistance of plastics, I borrow the one used by Alfredo Campo in 2008. Here, it is said that chemical resistance is the ability of a polymer material to maintain the original properties after being exposed directly in chemical environment for a specific period of time. Just to give you an illustration of this definitions, I make a plot of the y-axis there is property retention of plastics versus exposure of time. And plastics that has a poor chemical resistance is shown in the red curve there. Usually, as a function of aging time, the retention, property retention of plastics is decreasing dramatically compared to plastic that has good chemical resistance, which is indicated in the green curve. There are several automotive applications which require chemical resistance. The first row belong to the plastics that is being applied in internal combustion engine vehicles, and the second row belong to the plastics applied for electrical vehicles. So for plastics in ICE, usually, for example, the first example there is time chain tensioner. So this is the plastic that needs to be to have a higher resistance against engine oil. For coolant hose connector, for example, this is a plastics that needs to also be resistant against engine coolant. So 50-50 water glycol type of solutions. For the boots and bellows, it is usually plastics need to be resistant against alkaline environment that is typically present in the grease that you use for the boots and bellow for the CVG. For plastics used for electrical vehicles, usually we are discussing or we are dealing with resistance of plastics against coolants, engine coolants, or refrigerants. And for other type of applications that we can think of, for example, plastic that is in direct contact with fuel, with oil, and with other type of chemicals such as AdBlue, we can also think about what type of performance criteria for such a plastics depending on the chemical environment that they have. Now, why is it important to have good understanding on chemical resistance in general? So there are at least 3 reasons. The first one is related to the ability for us to choose proper materials, so for specific applications. And the second reason is to be able to better predict performance of plastics under certain operation conditions. So this is really intended to narrow down the number of tests. So if you know more or less what is the performance of plastics, then you will be able to also design a better testing that is also meaning that the number of tests can be lowered down. For us at DSM as a material supplier, we want to have a better understanding on chemical resistance of plastic in order to improve the performance of the plastic itself for certain applications. So without good understanding, the most straightforward way is typically we generate data with all possible scenario. So meaning that you have typically a matrix of plastics, a matrix of different type of materials, different type of chemicals that use to age the plastics, and the matrix that is, let's say, related to the different type of temperature and different aging time. So without any understanding, we can do all type of experiments, but typically this takes a lot of time and a lot of resources. So having good understanding is also useful to narrow down those, to have a better selection on what number of tests that we are looking at. The focus of today's presentations is not on the detail of chemical resistance of a specific polymer for specific applications, because if we go into that route, then we will only narrow down to a certain specific chemicals that might not be relevant to other audience. So here I consciously choose a more generic theme, meaning discussing a bit more on what type of typical challenges in conducting chemical resistance study, what are the basic principles of degradation mechanisms during chemical aging, and the third one is the important parameter which play a role in chemical resistance. So hopefully by choosing this more generic feature on chemical resistance or plastic durability study, it can trigger some discussion that we will have in the future. If you have certain questions for certain specific, let's say, chemicals for certain specific application, just email us, email me, and then we can discuss this a bit offline. What are the challenges in chemical resistance study in general? So before we go to that, let me present to you a little bit more on what type of typical chemical aging and testing that we do at our lab. So if you are doing chemical aging, usually we are using, for example, a standard representative form of plastics in form of the tensile bar. and we place this tensile bar in the sample tray, and the sample tray will be placed in the glass jars, and the glass jar will be filled with automotive fluids, and then we put that glass jar into the oil bath and increase the temperature, and we start aging, right? After a certain period of aging, we usually take the tensile bar out. We do post-treatment from time to time, depending on the situations, and we do tensile tests afterwards. The molecular weight analysis usually being performed, so additional analysis is being done depending on the situations. So in this case, we use molecular weight analysis using size exclusion chromatography, SEC, or you can also you also know it as a gas permeation chromatography, GPC, and other type of analytical measurements such as mass uptake, X-ray fluorescence, and microscopy. So in the next few slides, I will give you a little bit more example on some nuance in the aging condition that may play a role in the eventual result of your aging test. So the first example that I want to highlight is the importance of ambient environment. So when you do aging in nitrogen fertilized air, sometimes the result can be so dramatically different as is shown here. So this figure in the left shows the tensile strength retention of polyamide aged in SO-ATF at 150 degrees Celsius under nitrogen environment or air environment. As you can see, in nitrogen environment, there is no tensile strength retention reductions whatsoever, whereas when you change the nitrogen environment to air, what you see is within 200 hours, you reach already half lifetime of the materials. The same story for polyamide in dextran 6-ATF at 150 degrees Celsius in the right-hand side figure. In this case, the molecular weight retention is plotted as a function of aging time. In nitrogen, you don't see any decrease in molar mass, whereas in air environment, you see that dramatic decrease, especially in the first few 100 hours. So here, this is really highlighting the importance of ambient atmosphere during aging. The second example is something that is not that trivial. So this is related to the relative amount of polymer that you use during aging. So left-hand side figure highlighted the tensile strength retention as a function of aging time of polymer in ATF at 150 degrees Celsius. In this case, I show two different cases where the black indicate 28% of polyamide, meaning that originally when you start doing this aging, you start with 28% polyamide, so 28% polyamide and 88% ATF, versus the situation where you only use 10% of polyamide in the jar. And you can see actually when you use a lot of polyamide during aging, the tensile strength retention will be reduced less dramatically when you use a less polyamide, in this case 10%. The same situation happens also, for example, if you are looking at aging of thermoplastic elastomer, TPE, as a function of aging time in ATF. In this case here, we see that we plot the strain at break retention at room temperature. Again, the same story. If you compare the result between 10% TPE in oil versus 15% TPE in oil, the retention of 15% TPE is shifted slightly to the right-hand side in terms of aging time. So the TPE has longer lifetime. Now, one way to understand this is relatively simple. So you can imagine that when you start to age polymer in such environments like ATF, and as a function of time, there is more and more active species that is generated in ATF that start to attack the polymer. Now, if you have more polymer in the jar, statistically speaking, there will be less active species will be absorbed into polymer on average per sample. So what you see then, the samples or the polymer start to be degraded much later when you have much more polymer in the aging jar compared to the situation when you don't have a lot of polymer. So the second example, just highlighting the level of nuance and level of details that you need to to take care of during the performing this type of aging. Now, I have mentioned 2 examples, but there are a lot of different, let's say, factors that can play a role in eventual performance materials under certain chemical resistance study. So I give the 3 categories here. So the first belong to the material composition dimensions. As you can imagine, that different materials or different polymer will have different resistance. Sample shape and sample size also play roles. So thinner tensile bars, for example, will be degraded much faster than the thicker tensile bar. So design criteria for thickness is also very important in this case, because we need to make sure that we age the more representative samples during this type of study. The second category belongs to the aging conditions. So I'm talking about already nitrogen versus air. But also there are some differences in aging temperature, so it's something that you need to be aware of. I already talked about polymer to medium ratio before, so this is some effect that is not trivial but important. And I think the most important thing also different type of chemical agents. So if you are using different type of oil, some oils are more aggressive than the other. The third is related to the testing conditions. So beware. If you do testing on sample after aging, sometimes the performance of the dried sample versus non-dried sample can be quite different. And also beware also on the comparing different results from different testing temperature. So in essence, fair comparisons between chemical resistance data from 2 different sources. So if you have a data from 2 different sources and try to compare it, be very careful, because if you do not know exactly the aging condition used to generate such data, typically this data cannot be compared directly. So I always advise to anybody who do this, be very careful, make sure that you have almost identical procedures so you can actually compare 2 results directly. Now we have been discussing about degradations, but I want to highlight in the next few slides different degradation mechanisms of polymer during chemical aging. So if you're talking about degradation mechanisms, there are 3 things that can happen. The first related to the fact that the chemical reagents that used to age the polymer will start to dissolve the polymer. The second one is related to absorption of the chemicals into polymer. And the third one is related to the chemical reaction. So the polymers start to react with the reagents, and usually it leads to the degradation of the polymer itself and reduction in the properties. So for the first degradation mechanisms, dissolution of polymers, perhaps something that I can illustrate here with the object that is related to our daily life. So if you use this laundry or dishwasher detergent pot that is made of polyphenol alcohol, this polymer usually will be dissolved in water by design after several seconds. So this is a type of degradations that I'm talking about, dissolution of polymers in the solvent. So there are certain process for dissolutions, just for your information, and I'm pretty sure most of you know about this. So when you start placing a plastic or polymer in certain chemical reagents, what happens is that the polymers start as solid state, and reagents or chemicals start to be absorbed. And if this reagent is really good in dissolving the polymer, what happens is that the molecular weight, so molecules within the solid polymer state start to be swollen because there are some absorption of chemical in there. And after that, you have a disentanglement. And if this happens more and more and more, what you eventually have is the dispersion of this disentangled chain, meaning that your polymer is no longer in the solid state, but they will be dissolved by this reagents. So this process is easier happening for amorphous polymer than semicrystalline or heavily cross-linked polymers that we typically found in the thermosets. So in principle, there are several ways to predict whether a certain solvent or certain chemicals can dissolve a certain polymer. So one of the most popular one is to calculate the so-called solubility parameters, which is by definition or represents the cohesive energy density of a material itself. So this cohesive energy density is usually expressed in terms of van der Waals force, so dispersion force, dipole-dipole force, as well as hydrogen bonds. To make it a bit more tangible, when you calculate the delta parameters of polymer versus solvent, if the delta parameters of these two are alike or very similar, then it is most likely that the solvent will be able to dissolve the polymer. If the delta parameters, solubility parameters of the polymer and solvent are not the same, then they are likely not to be dissolved. So DSM has a repository informations on what type of solvent that can dissolve or what type of polymeric grades that we have. So if you want to know a bit more on this, please go to plasticsfinder.com. And in there, you can search for a specific, let's say, grade, for example, the G4010T, which is the PPS grade that we have, and click the chemical resistant or ChemRes button in there, and you will end up with a list of solvent that can or cannot dissolve that G4010T. So PPS in this case is really chemical resistance. Usually when you see that list, most of the time there are not so many solvents that can be used for dissolving PPS, and the solvent that cannot be used for dissolving polymer usually indicated as green arrow or green check in our plasticfinder.com website. So the second degradation mechanisms is related to the physical absorption of chemical. So perhaps just to illustrate this point again, with something that you can find at home. So if for you who are using soft contact lens, you must be very familiar with this. So if you have a silicon hydrogel contact lens, it's made of polymeric materials. If you compare their form and their feel when they are wet versus they are dry, then you can see that the difference. So wet soft contact lenses usually is rather round and rather soft, but as soon as you dry that contact lens out, and that will become brittle and wrinkled. So this is kind of a physical phenomena differences due to absorption of water in this case of soft lens that can play roles in the appearance and also the properties of the materials. So if you talk about absorption of chemicals, we are talking about three different parameters that play roles in this. So the first one is belong to the diffusivity. So this is in essence how fast the chemicals go into polymer. And the second part is how much the chemicals that can be absorbed in total. So we call this solubility limit. And the third one is just the multiplication of diffusivity and solubility limits. So we call this permeability. So permeability is very important parameters because this is something that can be easily measured using standard permeation tests. The diffusion and solubility can also be easily measured, for example, using mass uptake or weight change type of measurements. We can use also nuclear magnetic resonance, NMR, to study water permeation and other type of techniques listed here. For the first technique on measuring the diffusion and solubility of chemicals into polymers, I show here as an example. So this is a mass increase curve of different polyamide and PET and PPS as a function of time aging in water at 100 degrees Celsius. So this mass increase indicates the amount of water absorbed into this polymer. So if you look into the curve belong to 4,6, for example, the mass increase start to go up, and at a certain point it reaches a plateau value, and this plateau value is really indicating the maximum saturation limit and maximum solubility limit of water that can be absorbed into 4,6. The diffusion coefficient value you can actually measure by looking at the gradient at the initial data. So the gradient there is really related to the speed of diffusion of water inside such polymer. And usually we calculate this diffusion coefficient by applying a certain model. And in the right-hand side figure, it shows the first order Fickian type of approach that we usually apply to get the diffusivity value of such a curve. But you can also use other type of model for this case. Now, so far we have been discussing about the way we measure the speed of diffusion and the amount of absorbed water into polymer. Here, I want to highlight a bit more on the consequence of having absorbed chemicals, in this case, as an example, water in polymer. So the left-hand side figure is showing the stiffness as a function of temperature of polyamide in dry conditions and in the wet conditions. So the wet conditions is basically polyamide that has been placed in humidity chamber after 5, 24, and 50 hours. And you can see that actually the glass transition temperature of polyamide, which is shown as the first order reduction in the stiffness. So in this case, for dry polyamide, the TG is around 75 degrees Celsius. And when you start to wet the polyamide, the TG will go dramatically down below 0 degrees Celsius. So in this case, after 50 hours conditioning, we are talking about TG of minus 20 degrees Celsius. Now, what is the consequence of having this low TG? So in principle, when you do the tensile curve or tensile test at room temperature, when you are testing dry polyamide, as indicated in the middle figure here, in the black curve, so you measure the property of polymer below their TG. But as soon as the polyamide absorbs water and the TG goes below room temperature, what you measure is property of polyamide above its TG. So usually what you found is lower tensile strength and much more ductile material, as you see in the orange figure, orange curve. So to summarize, absorption of water into polyamide will result typically in TG decrease and decrease of stiffness, as well as increase in ductility because of the fact that you start to have more and more water into the polymer. And this phenomena also happens for apolar solvents like oil and other type of medium that usually exists in the automotive environment. So something that you need to be aware of. So the third, degradation mechanisms, is something that is the most important, and I think most of you knows about this, is chemical degradations. As an example, I show here this is the plastic hose that is being, let's say, used to channel hot engine oil, and after a certain period of time, what you see is there are some cracks on the surface of the plastic hose, as well as the let's say the embrittlement at the surface. So this type of when you do proper analysis at the surface, you will see that actually that surface is composed of lower molar mass plastics compared to the original plastic before aging. When we are talking about polymer degradations, the most well-known degradation mechanisms is hydrolysis. So in this case, here I show two different reactions. The first one belongs to the reactions between polyamide and water. So what happens that when water start to react to amide bonds, the amide bonds will start to be cut, to be cleaved, to form carboxylic acid end groups as well as the amine end groups. The second example shows the same thing. So ester bond from polyester react to water, and water start to cleave the ester bonds as such that we will start to have more and more carboxylic acid end groups and hydroxyl end groups that is being created as a result of hydrolysis. So the hydrolysis rate, or the higher rate of hydrolysis, typically happens at higher temperature following the Arrhenius behavior, and when acid or base is present. So can be acid-catalyzed or base-catalyzed hydrolysis for amide and ester bonds. So this is something that I think very popular, and a lot of people knows about this. So in the past, we also studied the mechanisms of hydrolysis of amides and ester bonds using quantum mechanics calculations. So what we do here is just to measure, or to theoretically predict the amount of energy needed during the whole hydrolysis process via several transition steps. And it turns out that the rate determining step, so the most energetic transition step that happens, belong to the nucleophilic attack of the carbonyl part of the amide bonds. And we use this, let's say, the energy needed to perform this transition step reactions as a, let's say, as a parameter to quantify or to measure, to calculate theoretical rate reactions. So we did a lot of different calculations for different type of chemical structure of polymers. And just to highlight here, so if you consider aliphatic polyamide in the right-hand side, top right-hand side figure versus semi-aromatic polyamide, it turns out that the reaction rate of semi-aromatic polyamide, the energy needed for the transition step is much higher. And we can make a link of that to the fact that the carbonyl, so the carbon of the carbonyl part, is less electropositive compared to the carbon of the carbonyl part of the aliphatic polyamide. So this type of theoretical calculation is really handy, especially if you want to design a new polymer, if you want to design a specific, let's say, polymer for specific applications, down to the level of molecular structure. Now, the next few slides is just highlighting the impact of, let's say, hydrolysis on polyamide properties. So the left-hand side figure show the molecular weight retention of polyamide after aging at 100 degrees Celsius at different pH levels. So pH 7, pH 2, pH 1. pH 1, maybe you can think about this as a conditions where it's very familiar during exhaust gas recirculation test. So EGR test typically is pretty acidic. And if you put some polyamide that is not resistant towards acid-catalyzed hydrolysis, you will have pretty fast degradations there. So this is just indicating that acid plays role in degradation. So the lower the pH, the more the acid, the faster the molecular weight going down of the polyamide. In this case, is polyamide 4,6. And this degradation in molecular weight or reduction in molecular weight also have a direct link to the tensile strength retention, as you can see in the right-hand side figure. So in essence, if you have a better chemical resistant polymer, then the molecular weight is more or less intact, and as a result, the tensile strength is also more or less intact. For a polymer material with a certain thickness, chemical degradation does not happen instantaneously throughout the whole thickness direction of the material. So we also need to take into account the speed of diffusion of the aggressive species from skin to the core. So just to highlight this particular important topic, here I show you some tips and some tricks that we do with our polyamide. So we actually compound pH indicator, in this case bromophenol blue, together with polyamide. And then after we make a compound, we injection mold into tensile bars like what you see in the left figure. So that the tensile bar will look purple because the bromophenol blue stay purple when the pH or ambient pH above 4.6. But as soon as you put the tensile bar into acidic solutions, you will start to see discoloration. So the yellowing from the skin to the core. So the yellowing really indicating the change of local pH from above 3 to below 3. And in principle, you can actually use this the thickness of the yellow layer as an indicator on how fast the acidic species goes into the polymer. And something that we also observe that wherever there is a yellow layer, there is also typically a low molar mass of the polymer, and also a crack start to be formed, and also pretty brittle materials that we observe when there is a lower layer band on there. So we do this for different type of polymer, and you can see that for polymer like polyamide 4,6, the ingress of acid is much more faster than for less polar polyamide like polyamide 410. So this is also showing or indicating that by changing the molecular structure, by changing the polarity of polymer, you can also to the long end limit their degradations via limiting the ingress of the active species itself. In the previous slide, we discussed about these important parameters for diffusions and also for the rate of reactions. And these slides show you a little bit more on the summary of what we do in terms of hydrolysis. So the left-hand side figure shows the solubility of water as a function of decreased polarity. So from left to right, you have a polymer that has decreasing level of polarity. So from polymer 4,6, which is very polar, to PPS, which is the less polar of the polymer grades that we have in our portfolio. So just looking at this picture, it's very clear that in order to have a better resistance towards hydrolysis, of course, naturally, you want to use less polar polymer. So instead of using polyamide 4,6, you use polyamide 410 or PPS, because all these three parameters are usually pretty low. So if you look into the solubility of water, diffusivity of water value, as well as rate of hydrolysis for PPS is comparably low compared to 4,6. And if all these three parameters are low, you by definition also have better hydrolytic resistance. So this is one of the example for aging in polar medium like water or acidic solutions. But you can also do the same thing for different solvents or different chemical reagent environments, such as engine oil, ATF, water glycol solution, and so on. So this is just to show you a little bit more of what type of parameters that is important and play roles in such environment in terms of their chemical resistance stability. Now we have been discussing about degradation of unfilled polymer, but what about glass-filled polymer? So I haven't mentioned that before, but this is just highlighting to you some of the principle that is important for this. So if you are talking about glass fiber reinforced polymer, what happens is that not only you have polymer, but you also have glass fiber and glass fiber polymer interface. So usually in automotive fluids, glass fiber is pretty inert. So you are left with two, let's say, entities that can be degraded: polymer or glass fiber polymer interface. Now, if you imagine that if you are, for example, using PPS, super high chemical resistant grade, usually what happens is that you don't degrade the polymer, but you degrade the polymer glass fiber interface. So if you're looking into this, if you overlap, let's say, the tensile strength retention of such a polymer versus the glass fiber reinforced polymer version of those, so we're talking about unfilled PPS versus glass filled PPS, Usually for unfilled PPS, you don't have a lot of reduction in tensile strength, but as soon as you introduce glass fiber where the interface is not optimized, you see that reduction. And this reduction is manifested by debonding, delamination, degradation of the interface. And usually, and this is already reported widely in the literature, so if you look into the glass fiber interface with matrix after aging, what typically happens is that there are some debonding between the glass fiber and matrix that as such that interface no longer carried load when we do some follow-up tensile testing. So something that we need to pay attention for. So we at DSM, we make a lot of improvements for our glass fiber reinforced PPS. In this case, left-hand side figure show you the tensile strength retention of reference glass-filled PPS versus improved glass-filled PPS as a function of aging time in water glycol at 135 C. So we make improvement at the interface as such that the retention is now going from the red curve into the green curve, so pretty stable. And if you look into the AFM figure or SEM figure, what you see in the right-hand side figure there is that for the reference GF PPS, as I said before, after a certain period of aging time, you see a debonding, whereas for the improved glass-filled PPS, you don't see any debonding, and it is translated to the increased tensile strength retention. To recap, just to summarize what we have been discussing so far regarding the degradation mechanisms. So typically there is a direct link between mechanical to chemical structure of polymers after aging. So when we are talking about aging of polymer in chemicals, what we start to see is usually a reduction in certain mechanical performance after aging, which is due to the decreasing of molecular weight. And if you have glass fiber in the compound, also decrease of the interface between the glass fiber and the polymer. And this is due to the absorption of the chemicals as well as the reaction of the chemicals to the polymer, or reaction between the chemicals towards the interfacial region of the glass fiber matrix interface, which is related to these three important parameters that I've been discussing about, so diffusivity, solubility, and the reaction rates. So if all these parameters are low, then you don't need to worry about the degradations. But if they are pretty high, then you will see the impact in terms of mechanical performance. And these three parameters is linked to the chemical structure and physical properties of polymer itself. So the intrinsic properties of polymers usually link towards their parameters and eventually to the mechanical properties. So at DSM, we are actually designing from the chemical structure, from the additives that we can make use of to improve the mechanical properties after aging via all this route. So we have this integrated approach, designing from the small towards from the structure towards the properties of the polymer at the end. So as a final slide of my talk today, just to summarize, what does better chemical resistance allow us to do so far? So I hope you are convinced now that if we have higher overall performance plastic, so we choose proper plastic for our certain applications within a certain environment for automotive, we will be able to then have more design freedom, meaning, for example, we can go to thinner part because we are now certain that the reaction rate is very low, the diffusion coefficient is really low, as well the amount of solubility limit of the chemical into the polymer is also low. So if all those parameters are low, we basically have a very good resistance of polymer. We also have ability to perform or to use these high performing grades for also make sure that we have higher weld line strength. So this is particularly important if you are considering the glass-filled polymer grades with a lot of weld line. And as you know, in the weld line, typically the strength is not determined by the glass fiber matrix interface, but intrinsically by the properties of the polymer itself. So if you have a polymer that is resistant towards degradation in that chemical environment, then it also translates to increased weld line strength. And the third one, which is important, which is related to why we use plastic in the first place for automotive, i.e. as a metal replacement, is time and again, when we do this chemical aging, the chemicals itself is really aggressive towards metal. By aggressive, I mean corroding, leads to corrosion of metal. So just for example, the right-hand side figure here, this is a type of, let's say, test that we have been performing where we have a polymer tubes with the stainless steel compression ring, and after a certain period of time doing chemical aging, we actually see a lot of corrosion in the stainless steel metal surface, but not so much degradation at the plastic. So it's kind of a reminder that we use plastics to replace metal, but also it brings added value because we are no longer faced by a corrosion issue anymore. So with that, I hope you enjoy the presentations. And again, if you have questions during these presentations, please use the chat functions, and you can also email me directly, and we can discuss a bit offline your questions. And thank you all for your attention. I would like to wish you a very good day.